For this lab, you will be looking at the capacity of various buffers and the effect of conjugate mixtures on the properties of a buffer. And so first we must define what a buffer is. You may have already covered this in lecture, but a buffer is a combination of the acid and base conjugates that are weak in nature that can interconvert between one another depending on external stimuli applied, like addition of strong acid or strong base. So I'm going to say that we have the acid and we have the base, but it's important that these are conjugates, and it is also important that they are weak. A strong acid and base combination would not result in buffer activity. Another important constraining factor for defining a buffer is that we also need the ratio of moles of the acid to the base to be within a certain range. And so that would be 1 mole acid to 10 moles base, or 10 moles acid to 1 mole base. This range is acceptable to be considered a buffer, but a lot of times we'll see buffers that are in a 1-to-1 mixture, and those are the easiest to work with in terms of predicting what their pH would be. Now, a formula is really handy for when we're describing a buffer solution. Technically, we could arrive at the same conclusion by a combination of ice tables for both the weak acid and the weak base in solution simultaneously, and adding together the concentrations of hydronium and hydroxide and figuring it out that way. But this is way simpler. The formula that we would use if we're thinking of it from an acid context is going to give us the pH. If we're thinking of it from the base component context, then we would get a POH out of the Henderson-Hasselbalch equation. So I'm just going to go ahead and write that that's what this is called, just in case. All right, so this formula, very important, can only be used with buffers. So you need to make sure that you are using a weak acid and its conjugate base, or a weak base and its conjugate acid, and that you are within the ratio range in order to be able to use the Henderson-Hasselbalch. If you only have a weak acid or only have a weak base and there's no conjugate present, this formula will not apply, and you can just use a regular ice table. All right, so the part that I've left blank here in the formula, if we're thinking of it from an acid context, we'll be using the pKa of the weak acid. So I'm just going to draw an arrow to that. The pKa of the weak acid plus the log of the conjugate base, A minus concentration, over the weak acid concentration, HA. If, however, we're thinking about it from the base context, I'm going to kind of draw a loopy arrow here to show that the pKb is coming from the base that we're using in our buffer solution. The POH is equal to the pKb of that base plus the log of, you'll usually see HB, like conjugate acid, and that over the base concentration. All right, now we're used to seeing these labels applied for whether like something is more commonly referred to as a weak acid or a weak base. Hopefully at this point we've started to kind of wrap our heads around the concept that whether we're calling it a weak acid or a weak base is kind of interchangeable in a sense. In a sense, the conjugate acid of the weak base, this here, is, maybe I should have my little pointer. The conjugate acid of the weak base is also could be thought of as a weak acid, and then this could be thought of as a conjugate base. This could be thought of as a weak base, and this is the conjugate acid. We could use these terms interchangeably, and therefore we could use the Henderson-Hasselbalch formula versions interchangeably in a sense. I'll rewrite this POH one just to illustrate that. So if we wanted to use our acid labels in the POH form, we could write the formula like this, where its concentration of HA over A minus concentration. So really, like, either way we could write this formula. These labels are really just to make it a bit more clear what we're talking about. Okay, so how does a buffer work is the next thing I want to address. So I've drawn this model to help illustrate how a buffer works. So in the first box, this is our buffer solution before we've added any strong acid, strong base to the solution. And you can add either strong acid or strong base and it will act as a buffer. And we'll explain what that means. So in this representation, I have A minus represented by blue circles, so my conjugate base, and my weak acid represented by the red dot with the blue dot combined. So that's to kind of show that the red dot is kind of like the proton, the H plus, that is attached to the A minus in the weak acid form. Okay, so that's my solution. It's about a 50-50 mixture. It might not be exact, depending on the ratio. But let's imagine a scenario where I add strong acid. And now in my solution, temporarily, when I do the addition, there are some red dots by themselves representing some of this weak acid, strong acid that we've added. So in that moment in time, the pH may be expected to be lower because now we have H3O plus or H plus just floating around in solution, but the buffer will immediately react to that. There are things around that can neutralize those H pluses, and those would be our conjugate base molecules that are sitting around nearby those H pluses. So the response, according to Le Chatelier's principle, is to, so I'm going to say buffer response is to neutralize that acid that we've added by forming more of our HA molecules from those red dots, from those H plus ions. And so now we have less conjugate base floating around in solution, but the overall impact on our pH is minimal. And that right there is the key determining factor for a buffer, or the key important property is that pH change resisted. It would have decreased slightly because now we have more HA relative to A minus, but it would not be a significant change, and that's extremely important for biological systems especially. So if we were to add, let's say we made a buffer solution, and let's just say we made it initially at this like mixture of conjugate acid, conjugate base that fell right in the middle of the buffer range, so like we started with a 1-to-1. If we begin to add base to our solution, we'll see the pH creep up a little bit, but then there's a point where it starts going up dramatically. And that point right there would be our point that we would identify as the edge of the buffer. So I'm just going to label this as broken buffer here at that point where it kind of the slope has an inflection point. In the other direction, as we're adding, let's say we started with that same solution and we started adding strong acid to it, the pH would slowly decrease. It's not a very dramatic slope because the buffer is resisting pH change significantly, but we get to a point where that pH starts to change much more dramatically. And so that point would also be a broken buffer in the other direction. So the distance between the 2 points where our buffer breaks, we will call our buffer capacity. So that's kind of represented here by the green arrow from side to side. There is a numerical way that we can represent buffer capacity, but we're not going to get into that right now. But it's also that region of the graph we will call the buffer region. My vertical arrows here I'm using to represent resisting pH change. Also, within the buffer region, we have the 1 to 10 to 10 to 1 ratio. So outside of that, our pH is going to change a lot more because it would be no longer a buffer. Something else that I would probably add to this part before I forget is that the within this buffer region, when we are right at that 1 to 1 point, we are at pH equals pKa. When 1 to 1. And we could see that from the Henderson-Hasselbalch formula, because essentially this log term would be 1 over 1. Log of 1 is 0, so that whole term would go away, and we would end up with a pH equal to pKa. Sorry, I'm not really illustrating very well. This whole term would go away, and pH would be equal to pKa at that point. So in addition to that, the pH being pKa when it's 1 to 1, we could also see that in the formula, the minimum and maximum values of that buffer region would be, so I'm going to say this is pKa. The maximum would be pKa plus 1 because of the 10 to 1 ratio. And the minimum would be pKa minus 1. So that's what you should expect to see for when your buffer would break, once your pH has exceeded or fallen below plus or minus 1 of that pKa value for the acid that you're comparing with. Okay, so that is kind of an overview of the conceptual. So now let's look at what you're actually doing in this experiment. So in this acid-base conjugate mixtures experiment, you will be planning and carrying out an investigation based on a selected research question. You're going to use the same set of acid-base conjugates that you used in the first part of this project. So that way you can carry on things that you've already learned about it and build that into your conceptual understanding as you do this experiment around buffers. So you'll select one of these research questions. How does the conjugate ratio influence the initial pH of a buffer? How does the conjugate ratio impact the buffer capacity? And how well does the buffer with equal conjugate concentrations protect against pH shifts in either direction upon addition of strong acid or strong base? So these questions are fairly similar, but what you would do initially while planning and carrying out your investigation is identify what is the independent variable that you're manipulating in the experiment and what is the dependent variable, and set up a data table that you can, put in the values that you're manipulating for your independent variable and your measurements for your dependent variable. So part of this will involve preparing solutions of buffers, and you have some guidelines to help in the planning process for that. You also have some guidelines for what to do in your actual experiment in terms of manipulating the sample according to your research question, so that you're able to measure the pHs that will actually be related to your question. But essentially, pH is what everyone will be measuring in this experiment. And afterward, you will conduct your analysis and argumentation. So just like last week, we have our buffer solutions. Well, okay, we didn't have buffer solutions last week, but we have our solution. And in this case, it's a buffer. And you'll likely be adding acid or base to it at some point for most of the research questions, but either way, you're using a pH probe to monitor the pH of your solution. After you've collected your data, you'll conduct an analysis and argumentation session with your group. And so part of that analysis is important to think of a way that you can plot or generate some sort of graph diagram model representing your data. And typically, let's remember that our independent variable usually will be on our x-axis, and we'll see our dependent variable on our y-axis. Because this experiment is much more autonomous, like your group is determining what you're doing for the experiment and setting up your own parameters for the most part with some suggestions, there will be a class presentation at the end after you have kind of conducted that analysis and argumentation. So you'll generate something that you can share with the class and open up an opportunity to get feedback so that you can make your argument even better before you're, submitting notebook pages or turning in some sort of report for it.